Okay, for our third example of relations, we're going to take a look at the same set as we did in the previous example, but a slightly different relation. So this time our relation between x and y is going to be defined as x is divisible by y. Okay, so populating our relation, can see that our first example is 2 and 4, and then 2 and 6, 2 and 8, 3 and 6, 4 and 8, and then 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, 7 and 7, 8 and 8. Now, interesting point. What you'll notice if you looked at the original, the previous example that I put up, is I haven't included in here the reverse of these divisions. Right? So we've said, okay, we've got 2 to 4, but we no longer have 4 back to 2, and that's just for the simple reason that 2 doesn't evenly divide 4. 4 doesn't evenly, but 2 does divide 4, but 4 doesn't divide 2 by a whole number. So that's why we've got all of these relations here. And for a change, we've got 2 mapped to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6. And you can probably guess right now, if you've watched the previous two videos, why I've included this set. Because the test for reflexivity, whether a set is is reflexive, is do we have all the x's mapped to themselves? And in this particular instance, yes we do. So we do now have a reflexive relation. Now we want to check whether it is symmetric. So again, this is if we have x mapped to y, then y is always mapped back to x. So we've got 2 to 4. Do we have 4 to 2? No, we don't. So therefore, we found a counterexample. This is not a symmetric relation. Now let's check whether it is transitive. Hopefully you're getting kind of familiar with the terminology by now, and again we're just checking if it's transitive by going x maps to y and y maps to z, then x, I always do that, x maps back to z, x maps onto z. So if we've got 2 to 4, we must also, we have 2 to 4 and 4 to 8, we also must include 2 to 8. Well, yes we do. If we've got 2 to 6 and 6 to 6, then 2 must also map back to 6. Well, yes it does. That's kind of a trivial example. 3 to 6 and on there, 4 to 8. So this is a transitive relation for the simple reason that we cannot find any counterexamples, any examples where this is demonstrably not true. Okay, so this is a transitive relation. And finally, we're checking whether it's anti-symmetric. Again, just as a reminder, our anti-symmetric condition is if x maps to y and y maps to x, then x must be equal to y. So we've got 2 to 4, and we don't have a 4 back to 2. We've got a 2 to 6, and we don't have a 6 back to 2. We've got a 2 to 8, we don't have an 8 back. 3 to 6, 4 to 8, 2 to 2. So what you can see here is this is an anti-symmetric relation, because we don't have any examples where this is demonstrably not true. We have a whole bunch of examples here where it is true, but none where it isn't, so therefore this is an anti-symmetric relation. And what you'll notice here is that because this is transitive, anti-symmetric, and reflexive, this is a partial order. Okay, so if it has these three properties, then it's a partial order. If it has reflexive, transitive, and it is symmetric, but it's not anti-symmetric, then that's what we call an equivalence relation. So this is a partial order, but it's not an equivalence relation.